Everyone. Welcome to the New Hampshire Audubon Red Barn Speaker Series. My name is Christian Robinson, and I'm the naturalist at the New Hampshire Audubon Newfound Center. I'm excited to have this opportunity to bring this event to you given these times. Thank you all for signing up and taking the time out of your night to learn more about our ever-changing climate. I want to thank our donor, Chris Locks, and our members for your support in our mission to connect people with nature, researching and conserving species in peril, managing 10,000 acres of wildlife sanctuaries throughout the state for habitat recreation, and advocating for sound environmental policy in the New Hampshire legislature. If you are a volunteer, member, or a supporter of the New Hampshire Audubon, we would like to thank you for your support. This program is made possible because of you. So again, thank you. Tonight we have a wonderful panel style presentation about climate change in New England. Our presenters, Dr. Lisa Donner from Plymouth State University and Dr. Janel Hanrahan from Northern Vermont University will be leading this talk from their professional expertise and their research. Lisa Donner is a climatologist and professor at Plymouth State University. She studies lake sediments to decipher past watershed changes. Her primary focus is on how climate interacts with other mechanisms for change, including natural catastrophe, as in fires, floods, landslides, and tsunamis, human disturbance, as in agriculture, logging, and development, and long-term trends like glaciations, tectonics, and sea level change. These projects are globally distributed with lake sites in Utah, Maine, Baffin Island, Canada, Iceland, and Turkey. Our other presenter tonight that I would like to welcome is Dr. Janel Hanrahan, who is a professor from Northern Vermont University. Dr. Hanrahan is an atmospheric scientist who uses statistics and computer models to understand how climate change is playing out on a local level, particularly with respect to the hydrological cycle. As the director of the Climate Consensus, a climate change education and outreach group, she is also interested in improving climate change literacy among atmospheric scientists and the general public. So I want to give a warm welcome and a thank you to both of our presenters tonight, and the floor is all yours.
Thank you very much. Can you hear me? Yes, okay. I'm going to share my screen to start my presentation. Come on. Okay, so thank you very much for inviting us to talk about this topic that is so germane today and very relevant to my life and Dr. Hanrahan's life. We thought this would be a great opportunity since climate change cannot be fully understood just from the perspective of the modern world or from the perspective of the past world, to combine these two and give as much time as possible for questions after our initial presentation. My presentation is going to concentrate on past climate, which will hopefully provide a perspective of what is the range of change that's possible throughout history and how much does the modern change compare to that. But it's not by any means going to be a comprehensive overview. I usually spend a semester talking about past climate change. And then there are full courses talking about modern climate change. So what we're doing today is we're just giving you that hint of what you might be curious about, and then we make ourselves available to answer your questions about that. So just a little bit of credentials for myself. The intro covered an awful lot of that, but I come to climate change mostly through the field of geology, but I do have a bachelor's degree, a BS degree from the University of Arizona in ecology and evolutionary biology. So I'm very interested in how climate and the human and natural life systems interact with each other. And I have studied in a lot of different places, from Turkey to Iceland to Venezuela, and then across the US from Utah to Maine. And I was born and did my undergraduate work in Arizona. So I feel in some ways maybe overly broad in my areas of understanding, but I think this has given me a good global view. Paleoclimatology, it's a fancy word. All it means is the study of past climate changes. And the reason we study the past is that the present is very complex, very confusing, very hard to understand the why of something that is happening. You know, why are 3 hurricanes in a year hitting Florida? Is that weird? Is that normal? How often is this likely to happen? So by understanding the past history of those kinds of events, we get a much better understanding of the present, and then we can project that into the future. Proxy climate data. The reason I put this slide up here is because if you do your own investigating about climate change, you're going to run into this word. And if you don't know what it means, it could be very a long haul trying to understand what the heck these are referring to. Proxy data is just another way of saying indirect data. So if you go and look at a thermometer and you read the temperature off of there, the mercury in that thermometer has risen up the tube as a direct response to the temperature around it. And so when you read the scale next to it, you're reading a direct measurement of temperature. But there are other ways of getting at temperature, and these would be those indirect or proxy ways. For instance, let's say you come across a patch of snow on the ground, and you are new to the area. You have no idea of the history of weather patterns in the area or what happened yesterday. All you know is that there's snow on the ground right now in front of you. Well, that tells you that when that snow fell, the air temperature must have been at least 32 degrees or colder. And because the snow is still on the ground temperature must have been conducive to leaving the snow there and not just melting it all off. So that presence of snow itself is an approximation of temperature. And you know, accumulations of snow, such as glaciers, will give you a sense of how long that snow condition has been present. And so you can extend out that proxy over time. There's chemical measures that are very, very precise. There's a lot of other kinds of proxy data. Which way a shell coil goes, whether it coils to the left or coils to the right, those are temperature dependent changes. And so there's a huge field of research that is looking at proxy climate data and making interpretations about it through the past. Now, the causes of major climate changes through time, I'm going to run through these quickly because I don't want to spend a lot of time talking about these. But if you have never had a geology class, then these are a useful review. Continental drift is caused by circulations of the magma underneath the solid crust of the earth that push that crust around. And it causes our continents to shift location over millions of years. And as those magma coils circulate, they can also collide to cause oceans to form. So the basins will open up and the water will fill it. And where all of those interactions are occurring, you tend to get a lot of volcanism, so volcanoes. And volcanoes, when they erupt, they emit, the magma has a lot of CO2 in it, and they release the CO2 into the atmosphere. So when there is a lot of continental drift and ocean basin formation happening, and also other kinds of volcanism, we tend to see periods of time when there's more CO2 entering the atmosphere. And CO2 is linked to warming. It's a greenhouse gas. So when there's more CO2 in the atmosphere caused by volcanism, then you're going to see a warmer planet. But there's a counteracting effect that the plate tectonics, the movement of these continents, also creates. So when two continents run into each other, you get mountains that accumulate. So Tibet right now is increasing in elevation because the Indian continent is running into the Asian continent, and that collision is actually lifting up the land. When mountains form, there's an excess of land mass that wants to erode and is reacting with the atmosphere around it And those chemical reactions and those physical reactions actually combine to remove CO2 from the atmosphere. It's a chemical reaction. The CO2 gets pulled out of the atmosphere, ends up in the water runs down the mountain streams and ends up in the ocean. And then in the ocean, that CO2 reacts and it forms shells, calcium carbonate. And that's how our coral reefs get formed. All of that CO2 that ends up in the ocean, a lot of that gets used by the life living in the ocean, and then that life dies and it sinks to the bottom of the ocean and it gets buried. So we have volcanism creating CO2 in the atmosphere and mountain building that pulls CO2 from the atmosphere. And it's kind of a push me, pull you, but over the time period of the Earth, it tends to be in a balance. So there's just small changes that will cause these periods of warm and periods of cold over the 4 billion years of Earth's history. Another thing that affects climate on Earth is, of course, the sun. You will hear on chat rooms and in scientific discourse also a lot of discussion about the role of the sun in affecting climate. And yes, of course it does. Today, I was sitting outside. It was a hot day. It was very sunny, and then a cloud came across the sun and it cooled dramatically. Well, these small changes in the amount of sun's energy hitting the Earth, they get averaged out from day to day, night to night, week to week, month to month. On average, over the entire course of a year, and year after year after year, and decade after decade, and hundreds of years after hundreds of years, the change in the total amount of energy coming from the sun to the Earth changes only by like 2 or 3%. And that is not enough to account for all of the changes that we're seeing in temperature today, but it is enough to count for small changes that we've seen in the past. And we know about those changes and we can attribute them to solar activity. The final thing that I'm going to talk about is just greenhouse gases in the atmosphere. I hope everybody here knows that the more greenhouse gas there is, the warmer the atmosphere, because those greenhouse gases physically trap the heat. They act as a sort of a holder of that solar energy, and they re-release it to the atmosphere instead of letting it escape to outer space. So when there's less concentration of greenhouse gases in the atmosphere is colder, the land is colder. When there's more, the atmosphere is warmer and the land is warmer. Over long periods of time, we can see these changes. So we have, let me talk about this chart a little bit. The beginning of the Earth 4 billion years ago, or giga years ago, that's why it's a G, is about when the Earth solidified. It's actually 4.5 billion years ago. The very early Earth had a lot of CO2 in it and almost no oxygen. And when plants evolved, photosynthetic plants evolved, they started pulling CO2 out of the atmosphere, turning it into plant matter, and then it was sinking into the sediments of the ocean. And as that occurred, the atmosphere cooled from that really warm early Earth to actually into a glacial period. And everywhere there is a yellow arrow here is where the temperature dropped below the threshold where glaciations and polar ice caps could occur. So the longer the period of being below that line, the longer the interval of sort of an ice house condition on Earth. And everything above the center line here, the center line is just the average condition of Earth today. Everything above that is a warmer Earth than today. And if you look at sort of sit back and look at the whole thing, you'll see that most of Earth's history is warmer than today. But there are distinct periods of those colder intervals, and every single one of those is associated with mountain ranges um, when they first developed and started uplifting. So we have a good explanation for why the cold periods were there. We don't have quite as good an explanation as to why the warm periods are here, except that we know from studies of continental drift during different periods of Earth's history that were especially warm. There was a lot of shallow seas where you could trap heat in the oceans. The continents were also mushed together a lot more than they are now, and so there wasn't as much circulation of that heat away from those continental areas. And so this was the time of the dinosaurs, when you see lots of pictures of swamps and ferns up in the Canadian Arctic. There was palm trees growing up there. There was alligators living on Antarctica. Much, much warmer world than today. But when we talk about continental drift and the volcanic processes that emitted CO2 into the atmosphere, this is not a fast process. We're talking 1 to 4 in a year, but over millions of years, that create the change in the position of these planets, of the continents. And so none of these are sufficient to account for what's happening today, but it does account for changes over long periods of time in Earth's history. And when we talk about the magnitude of change over Earth's history, from the warmest of the warm periods after the Earth cooled, what we have, after the crust cooled off, what we're really seeing is about 9 to 14 degrees Fahrenheit warmer than today. And then the last ice age, the coldest estimate for how the average temperature of the Earth was 6 degrees colder than today. So we're talking about a range of 20 degrees Fahrenheit from the warmest period to the coldest period. This tells us that the Earth is extremely sensitive to even 1 degree change in temperature. And that's why there is concern about 2 to 4 degrees or 6 degrees changes of temperature. The Earth is very sensitive in terms of how much ice it builds and how much ice it loses. This graph is a little bit complicated, but it's still set up the same as the others, where on the left side is the older part of the Earth, and on the far right side is today. And this is a temperature curve. So we can see that warmest period in the green cooling down steadily until about 4 million years ago. The scales at the bottom changes. So it's millions of years on the left and then thousands of years on the right, just so we can see more detail. So as the Earth cools, it starts going into a period where there's a lot more fluctuations between warm, cold, warm, cold, warm, cold. And this red line in the middle, again, is today's average temperature. So this is what was the Earth compared to today. And about 3 million years ago, the temperature of the Earth dropped below today's average temperature. And it didn't really come back to it except for very short periods of time. And when we start looking at the sort of electric blue curve here, and you see those really high swings from cold to warm, but most of it is in the cold period. These are a series of ice ages that began about 3 million years ago and shifted in their behavior, so that about 900,000 years ago, less than 1 million years ago, the dominant condition of the planet was to be in an ice age, and the minority condition of the planet was to be in what we call an interglacial, or a between the ice age period, like we are now. We are in an interglacial period right now, in between ice ages, in between glacials. And those interglacials usually last only about 10,000 years. They go very quickly from the coldest interval to a very warm interval, the ice disappears really quickly. And by really quickly, I mean within about 4,000 years, you can shift from a majority of ice over an area to no ice over an area. And then it almost immediately starts to cool again. So we see this sawtooth form of going from the coldest period of the ice age very rapidly to a much warmer planet, and then it starts to cool almost immediately. And when we look at this last panel here on the right side, that's the last 10,000 years. And again, that red line is today, and then the little red dots on the far axis over there are the projected temperatures for the future. So if you take the height on that right axis, where it says 2050, in 30 years, this is one of the projections of a temperature of about +4 degrees Fahrenheit. You have to go back 150,000 years into the Eemian to find a temperature as warm as that. And then if we look at 2100, which is 80 years into our future, you have to go back 10 million years or more to find a temperature as warm as that. So last thing I'm going to talk about is sea level. When we have a glacial period, there's about an average of 30% of Earth's surface that's covered by ice. It changes from glacial period to glacial period. The last one, 30% of Earth's surface was ice. And the difference between that and today is equivalent to about 400 feet of sea level rise. So between 20,000 years ago and now, sea level rose by 400 feet. We have about 10% of the Earth still covered with ice, or at least we did prior to this century. That's starting to decrease rapidly. And if we lost all of that remaining ice, that would be equivalent to another 230 feet of sea level rise. Now, don't freak out. Nobody's actually expecting that to happen because there's a lot of checks and balances in the way the Earth responds. You know, when sea level increases, it changes the thermal capacity of the Earth. So things can't warm up as fast. You don't melt as fast. But the important thing is that sea level is rising. It's rising in response to the loss of ice. Last thing I'm going to talk about is carbon dioxide, because we have to tie carbon dioxide into this story. It's a key player. This is a graph showing the record over about 25 million years created from proxy data using carbon chemicals, forms of carbon that are in fossil plants, and looking at the temperature association with those particular carbon molecules in these fossils. And you can see that the solid green line in the middle is the median estimate of CO2 levels that must have been in the atmosphere when those fossils were formed. And the lighter shading is the uncertainty of how much CO2 might have been in the atmosphere at the time when those fossils formed. So the uncertainty, you know, if you want to take the most generous view, then look at the uncertainty curve, and that there is about from 200 parts per million to about 500 parts per million maximum. Now look at the red star on the far right side. That's the value of carbon dioxide in the atmosphere last year. And then the bars above that is the value for 2050 and the value for 2100. So, you know, as we go into the future, we enter a world where the CO2 levels are much higher than at any time in the recent past, for sure, and perhaps any time in the predictable past, like our era. If we zoom in a little bit, and we can look at the direct measurement of CO2 trapped in ice bubbles from Antarctica, We can actually measure how much CO2 was in the atmosphere over the last 800,000 years. That's the upper graph here. 800,000 years ago is on the far left. The modern era is on the far right, and you may not notice it, but the farthest right before you run into the axis, there's a line that jumps up there, and that's actually today's value. Let's see if I can move this out of the way so you can see that. Yeah, this value way above 400 is today's value. So you can see in the last 800,000 years, the events from ice bubbles in the Antarctic ice that CO2 has ever been this high. If we look at the last 10,000 years, which is the bottom graph here, you can see that the variation in the last 10,000 years is really small compared to the change in the last century. And finally, if we look at the last 200 or 300 years or so, we can see that the really rapid increase in CO2 in the atmosphere started occurring about the Industrial Revolution around, the late 1800s, but it really ramps up after World War II, when the modern era kind of begins and massive uses of electricity and massive generation of electricity really started going. And then also the use of automobiles became, everybody had an automobile, at least in the US, by the 1950s. Most families had automobiles and started driving a lot. And the very bottom chart, most of you have probably seen, this is the measurements at Mauna Loa Observatory in Hawaii, showing you the change from 1958 until today. It actually, I think the data is from, June 28th, the last dot on here. And the little zigzag part is the winter-summer couplet. So in winter, when the trees are not out in the northern hemisphere, CO2 accumulates in the atmosphere because the trees aren't pulling it down. And as soon as the trees leaf out, they pull CO2 out of the atmosphere and it drops. And then in the fall, it starts to climb again, reaches a maximum in the winter, and then in spring, it starts to drop again. So, but the important part here is that the trend is upward. Every single year, the trend is higher than the year before. Okay, that is the end of my part of the talk. I'm going to stop sharing and turn it over to Janel.
I'll go ahead and unmute myself and get my screen shared here.
So I do have one clarifying question from Chris. CO2 or CO2 equivalents on graphs?
Well, I think it's a direct measurement of CO2. But that's more of a technical question than this geologist can answer.
Sounds good. Thanks for the question, Chris. And thanks for your response, Lisa.
All right, so hopefully everybody can see my screen here in this picture of our beautiful home. Can everybody see my screen okay? I could just get a couple of nods. Okay, great. So I wanted to start with this slide that almost looks a little blank here because I just have a picture on it. But this is a really important one just to set some context. So as you guys know, this is our planet Earth, and here is our atmosphere, which is this blue kind of hazy line that goes around it. And of course, here we can see the sun rising over Earth. And this seemingly insignificant little blue hazy line here is the difference between having life on our planet and not. And if we didn't have our atmosphere, our planet would simply be too cold for life. The temperatures would swing drastically and we would not be able to have life on our planet. In addition to that, if we didn't have greenhouse gases in our atmosphere, our planet would be too cold for life. And so this just shows that our atmosphere, as seemingly insignificant as it is for someone kind of looking at it from the outside, if we change it in any way, it can have a pretty big impact on what's going on down here on the surface of the Earth. So for my presentation, I'm going to be walking you through some graphs, but also some maps, because I am a climate scientist who studies today's climate system and what happens in the future. And I do that using observation data, statistics, and models, because we have to use models to try to understand what's going to happen moving forward. So I'm just starting out right here, and I think this is classic, actually. I don't know, you probably can't see, but it's pouring rain here right now, so I'm hoping this isn't going to wreak havoc on my internet connection here. But this is just taking a look at projected changes in annual maximum precipitation. So in other words, extreme precipitation. On the rainiest days, how much it rains. Taking a look at the end of the century compared to the end of last century. In the greenish areas here, the darker green areas, means that that intense precipitation is going to increase. And we can see that that's pretty much the case all across North America. So I figure what I would do is, instead of using pictures, I would use a map to tell you a little bit about myself, because I do think it's always very important to let your audience know who you are, and I guess what your credentials are, to let people know. Because sometimes when it comes to topics like climate change, everybody seems to be an expert, and so I think sometimes it's good to let people know that you actually are. So I actually earned my bachelor's degree in mathematics. So my formal training is in physics, computer science, mathematics, and that's really how I found the field of atmospheric sciences. I ended up earning my master's and my PhD at University of Wisconsin-Milwaukee. And while I was there, my primary research was taking a look at how the Great Lakes water levels are impacted by climatology. And at the time, when I first came up with this question, it wasn't about climate change, it was about climatology. And so I was really interested in things like El Nino Southern Oscillation, North Atlantic Oscillation, so some of these natural climate oscillations. And I wanted to know, what is it that makes the water levels go up? What is it that makes the water levels go down? And when I walked into this, I knew very little about climate change, human-caused climate change. And quite frankly, I wasn't really that interested in studying climate change. I just wanted to know more about the statistics of weather, and I wanted to try to answer this question. Well, what I found out rather quickly when I embarked on this journey is that climate change, human-caused climate change, is greatly impacting the water levels of the Great Lakes, and also how the lakes respond to regional weather. And I won't go into the details of that, but I will say that the Great Lakes have lake level data that go back to the late 1800s. And what I found was an abrupt shift in all of my data sets at about the year 1980. So after about 1980, things really started to rapidly change. And so we ultimately ended up publishing a few papers connecting the Great Lakes water levels to human-caused climate change. So that was all observational analyses. The next thing I did was I accepted a research position up at the University of Alberta. So I was hired under a grant that was paid for by the city of Edmonton, who hired me to do some modeling work to essentially give them future precipitation data on which they could redesign their hydrologic infrastructure for both the city and much of central Alberta. Because what you can see here is that it's also projected that extreme precipitation is expected to increase in that area. And what they had been seeing is pretty catastrophic flooding all over in Edmonton, Calgary as well, which is about 3 hours to the south. And so they really wanted to address that by essentially obtaining future precipitation data that they could use to redesign the entire hydrologic infrastructure. And I always think it's fun to share a case in point when my husband and I packed up everything that we owned and adventured up to Alberta, Canada. Neither of us had ever been there before, which is sometimes what you do for a postdoc position. We loaded up everything we owned in this U-Haul trailer. My husband drove his truck. I was driving a car behind him. And there was record floods all over in the northern part of the United States and the southern part and southwestern part of Canada. And we ended up having to drive through a lot of it. And so this is actually a highway, a main highway somewhere in Saskatchewan. I don't know for sure where it was. But it was open because people had to get from point A to point B. And I, for whatever reason in my younger years, thought it was a good idea to pull out a camera while driving through a flooded road to take a picture of my husband in front of me. But I just like using this as an example that I'm truly living some of my research sometimes. So while I was there, again, I was really taking a look at how climate change would impact extreme rainfall in central Alberta. And this was really my first opportunity with being able to run climate models. So it was a really great experience for me. So next up is Northern Vermont University, Linden. When I started there, it was actually Linden State College. We recently changed names, but that's where I am today. And my work there really encompasses climate change, how it impacts weather, primarily related to the hydrologic cycle. So taking a look at precipitation, extreme rainfall, things like that in the Northeast. Also taking a look at things like cloud cover, the lengths of seasons. And so I continue to use a climate model to try to understand how things have happened in the past and how things are going to continue happening in the future. And then just a fun fact, the climate models that I run, the regional climate models, I actually don't run them in-house because they're just too complicated and it takes too much data. So I actually run everything on this supercomputer that is located in Wyoming that's owned by the National Center for Atmospheric Research. So I actually run it right from my office in Vermont, and actually for the past few months I've been running it right here from my spare bedroom in my house. So this is a graph that is very similar to one that Lisa just showed. It was actually kind of the subsegment of one and then at the end of another one. But I just briefly want to talk also just to set some context, take a look at the paleo record. And this graph only goes back 400,000 years, so about 500,000 years. Lisa talked really great about going back and forth between these glacial, interglacial periods and how different the climate was between those two. But what I want to point out here is that carbon dioxide ranged naturally between about 280, 190 parts per million over this period in time. And today, I actually just checked yesterday, we are currently at 417 parts per million. This goes up somewhere between 4 and 5 parts per million every single year. So this is continuing to go up. But what you'll notice here is that the current global temperature seems to be lagging far behind that. So that's sitting all the way down here. And so, well, I hope you don't mind. My husband and my 6-year-old son are wrestling in the other room. So I'm hoping you're not picking any of that up, the joys of presenting from home. So in any event, so temperatures are still sitting quite low. And we like to think about that, and when I say we, I talk about my students and I, because we're always thinking about analogies. We like to think about it as the earth being essentially a big loaf of bread that's in the oven. And what we've done is we've essentially just taken our earth and we just put it in the oven and we just started turning the temperature up. And so the current temperature setting right now is about 417 parts per million. But we just, on a paleo time scale, on a geologic time scale, we just put our earth in the oven. And so there's a lot of heating that still needs to continue. And oftentimes we refer to this as heating that's in the pipeline. But we are in fact heating up. So this slight little uptick right here is now illustrated here by direct observations. So we have pretty solid global temperature observations going back to the late 1800s. And we do in fact have this uptick in global temperatures. And we can see that before this big uptick right here, we had a lot of natural climate variability that has to do with the way that the ocean overturns, all sorts of natural climate fluctuations. But most studies now have concluded that since about 1950 or 60, that this predominant trend right here is in fact driven by human-caused increases in greenhouse gases. And so that's really the research that I do, is I try to take a look at what's happening here with this increase based on what we've seen already. And then I try to take it to the next step where I use climate models to try to understand what's going to happen here as we come up to temperature. And also this 417 is a moving target. So as that continues to go up, what's going to happen on a regional scale? So I'm just going to walk you through some global impacts of warming and then kind of bring it down to a local scale, because I know we want to talk about what's happening in the Northeast. Global impacts of warming, of course, we know rising temperatures. So we're seeing this on a global scale, but we're also seeing this in individual locations all across the world. If we just take a look here at the United States, we're warming pretty much everywhere. There are some pockets of cooling. And so we have some regions here that's kind of in the Gulf area that has actually been cooling. That's a very active area of research right now. But the story here in the Northeast is pretty much warming across the board throughout the year. Most of the warming that we've been seeing has been during the winter months. Also, impacts of global warming are more or less precipitation. So general rule of thumb is that wet regions are getting wetter, dry regions are getting drier. So here in the Northeast, we tend to be a wetter region compared to other regions. So we can see that kind of the entire eastern half of the United States, especially the Midwest and the Northeast, have generally been getting wetter, whereas a lot of the regions in the West have been getting drier. We've been seeing more precipitation, particularly during the summer months and then during the fall, but also a slight uptick in some regions during winter and spring. In some regions, we're experiencing more drought, and perhaps counterintuitively, and this is actually a projection, but observations are starting to support this. Perhaps counterintuitively, in this region here in the Northeast, where we just said that we're going to have more precipitation, or that we've been seeing an uptick of precipitation, we're also going to likely be seeing more drought. And so you might be wondering how that's possible, but the idea is that the way that precipitation falls is changing in time, so that when it rains, it really, really rains. But then you get these long dry stretches where you don't have any rain. In fact, we've just recently seen that here in the Northeast. I know in New Hampshire and here in Vermont as well, where we were in drought conditions. And now it's been raining really intensely for the last couple of days. And so it's kind of like all or nothing what we're seeing, but we are expecting to see some drought and extreme precipitation increasing sometimes in the same area. And that's the story essentially for our region. Just flying through a couple of other impacts here, more wildfires, not likely to increase here in the Northeast, but definitely out west and in some other countries. Sea level rise, like Lisa already talked about, and then new, in my mind, very interesting weather patterns and stronger storms. So my research really starts to dig into some of these smaller scale processes that have to be resolved with what we call regional climate model to try to understand how this is going to change under global warming. Some of these things have already started to happen. We're hearing about more extreme weather events, some just kind of strange storms in general. In some cases, more severe winter weather, a lot of flooding, more ice storms than we've seen in the past. In one of my classes, it was my class for non-science majors talking about climate change. One of my students, I think, put it really well, is he said, okay, so global warming just causes more of everything. And he was talking about this idea that because we have more energy within our climate system, we're just seeing more extremes of everything, more precipitation, more drought, bigger storms. And so I thought that was a really good way to put it. Here's a time series that actually shows observed temperatures. This is similar to one that I just showed, which is the black line. And then moving into kind of the modeling world, which is just using equations to better understand our climate system, is the gray line. And when we run a climate model, we don't expect to say that there's going to be rain or that the temperature is going to be such and such on a certain day. But what we do instead is we talk about statistics and trends. So a good example of that, if you're moving from spring to summer and the temperatures, you would say, from a climatology perspective, that temperatures are going to increase through time going into summer. But I have no idea what the exact temperature is going to be on a given day or when it's going to rain or not rain. All I can do is talk about statistics. And so we can see here that the model actually does a pretty good job when it's initialized in the late 1800s to align here with observation. So what I want to point out here is that everything that we've seen so far, all of this more that we're seeing, more extreme precipitation, more drought, everything that we're seeing is a direct result of this uptick here and this increase in global energy, right here, again, since about 1960. So on this graph, and I'm really hoping that the animation comes across here. Here I'm using kind of the latest and greatest of some of the climate models that are starting to come out now that are going to inform the next IPCC report, which will come out in the next couple of years. What we can see is that we essentially have two future trajectories. Of course, we have an infinite number of trajectories somewhere in between here. But oftentimes you hear people say, well, our climate has changed, or we're in this new climate system. I'm gonna throw out my arms. There's nothing I can do. The problem is too big, what have you. But what I like to remind people is that what we have seen so far is this uptick right here. So about 2 degrees Fahrenheit over what we had during pre-industrial times. But moving forward, there's a huge spread still in terms of where we end up. So this current trajectory is oftentimes what we refer to as business as usual. So we keep burning fossil fuels. We're not efficient with our energy. We don't conserve energy. And we just decide that this is something that we don't want to address. And this is where we end up. And clearly what you can see is that issues that we have with the intermittent precipitation and increasing temperatures and increasing droughts and increasing strength of storms, all of those things are going to be amplified substantially if we continue on this current trajectory by the time we get to the end of the century. The alternate trajectory, and this is important to note, we are not likely going to go back to the same climate system that we have all grown to love over the last several decades. So we're going to be sitting right around the same climate system that we've already created here. So in the end, we need to adapt, but we still need to mitigate. Both of these things are extremely, extremely important moving forward. Let me just click forward here. So again, I'm hoping that this comes through for you. So again, using those same climate data, for those of you who are a little more spatially oriented, I think that this is a really good way to visualize the kind of the differences between these two possible future scenarios. So on the left-hand side is what we consider a renewable energy future. So we stop wasting energy. We figure out ways to get energy that's not fossil fuel, that's not coming from fossil fuels, not carbon intensive. And then we also figure out a way to get carbon back out of the atmosphere, which we don't actually have large-scale technology for that right now. The right-hand side is, again, that fossil-fueled future. We just decide that we're going to continue business as usual and not really do much about it. I think this is important because you'll see at the top I put age of person who's born in 2015. So as I mentioned before, I have a son who is in the other room wrestling with my husband, and he was actually born in 2014. But I started this one in 2015 because this model run actually started in the year 2015. And so I thought it was important to attach an age to this. And the reason I say that is because while all of us will be probably long gone by this point, there's a whole generation that's being born today that's going to be living through our decisions that we make right now. A couple of days ago, we had some severe weather coming through, and my son had told me that he was afraid of the thunder. And I, of course, as an atmosphere scientist, had to sit down with him and show him all sorts of diagrams to explain to him where the thunder and lightning is coming from and everything. And he looks at me and he goes, "Mom, how come you know so much about weather?" And I said, "Well, it's my job. That's what I teach. I need to know a lot about weather." And he looked at me and he thought for a little bit, and he goes, "But I thought your job was to save the world." And while that may seem pretty grandiose, he's seen me advocate for climate change action and all of that. And it occurred to me that for him it really is. This is his world. This is his entire life, because at this point he'll be 85 years old, assuming he lives a nice long life. So I think it's important for all of us that when we're thinking about our kids and grandkids, that we keep all of this in mind, that our decisions today really truly will make a huge difference tomorrow. And I don't want to take up much more time because I do want to open it up for questions, but I just want to give a real quick shout out to the Climate Consensus, which is a group that started in 2014. It's very much student-led, but also department-run, where we teach upcoming atmospheric scientists how to get out and engage with the public and talk to them about the science of climate change, because it's something that a lot of people don't understand, and we are never going to end up at that lower scenario unless people really start to understand what's happening. Last thing I have here is just a whole bunch of information, data sources. I figured I'd throw this up here in case someone wanted to just take a quick snapshot with their phone, or if you want to go back to this later on, or if you just want to contact me, I'm happy to provide you with some of these resources. And with that, I'm going to go ahead and stop sharing my screen. And I think, Christian, are you going to take over here?
Yes, I am. So we're going to leave it open until about 8:15 for questions for our two panelists. You can either type it in the chat or raise that blue hand and we can call on you.
And if people are willing to share their audio, that would be great too, because it's really nice to be able to see people that we're talking to.
Oh, Lisa, we did have one more from Chris. It was about the first question he asked. He mentioned permafrost releasing methane is my concern in that graph that you had at the end. Is that in the graph?
The graph at the end of the projection. I think what I was showing was probably including methane enhancement as a greenhouse gas, but there's still a lot of uncertainty about how the Arctic is going to respond because so methane is something that is created when plants decay. And there's a lot of decaying plants trapped in the permafrost, and the gases that are released from that decay are frozen right now. They're trapped in the water, in the frozen soil, in the frozen earth. But as the northern regions and the southern regions of the world warm, that ice in the permafrost turns to liquid, and then the gas bubbles can be released. And a lot of that gas is CO2 and methane, as well as oxygen and other things. But the methane is a really strong greenhouse gas compared to CO2, and it has a much bigger impact on warming in the short term. And so there's a lot of study and a lot of research going on right now about how much methane is being released compared to how much methane is being reabsorbed by bacteria and other organisms that use that as an energy source. So again, there's always a push me, pull you whenever there's a resource that's made available. And that story is still unfolding, but I think there's a great deal of concern among climate scientists that methane from melting permafrost is going to be a big player in the future.
And from a climate modeling perspective, because I think it was the graph where you showed the projection, the temperatures, right? Mm-hmm. And I just want to mention from a climate modeling perspective that when there are things that are not really well understood, so especially feedback mechanisms, something like methane release, we tend to err on the side of being conservative. And so oftentimes those estimates in terms of temperatures resulting from increases in things like carbon dioxide, oftentimes we're not fully taking into consideration some of those feedback mechanisms.
Thank you both. I'm going to unmute David. He has a question. One second.
Hi, it's Mavis, and I wanted to ask a question of Lisa. I was way back, you talked about temperatures, and way back, you know, millions and millions of years ago, and I don't understand how you determine the temperatures from that long ago.
Okay. There's a number of ways that we can do that. The simplest way is actually using plants and animals that are found as fossils in the rocks that were deposited and formed at those times. So let's say 65 million years ago when the dinosaurs were around, besides the dinosaurs, there's also lots of plants that got fossilized along with them.
Okay.
And we know what kinds of climates those species of plants can survive in.
Mm-hmm. Okay.
And so we can use today's version of those plants as an example of, well, they lived in the tropics. So therefore that area where that fossil was found must have had a tropical climate.
Well, thank you.
Thank you, Lisa. The next one we have is from Michael in the chat box. I'm interested in local impacts of climate change. What might we see in New Hampshire and Vermont specifically? Could you provide some examples, things like shifts in the maple industry, etc.?
Yeah, so I can take that one. And the first thing I would say is I would refer you to the National Climate Assessment Report. It's an excellent comprehensive report that is, for the most part, in plain language. And so I think it's accessible to most people. And the website is really, really nice. So again, it's a national climate assessment. There's volume 1 and volume 2. Volume 2 was the one that came out, let me think, about 2 years ago. And volume 2 would be the one that would be of most interest to you because it talks about climate change impacts in the United States by region and by sector. And so it's a nice way to really dig into something that's very specific to what you might be interested in. But just to tackle that one briefly, in terms of changes that we expect to see in New Hampshire and Vermont, again, warming, more extreme precipitation, which again is seasonally dependent, as you can see in some of those maps that I showed you. In terms of snowfall, perhaps counterintuitively, it's thought that we may actually be located in kind of a sweet spot, at least for a little while, because more precipitation means more snow if it's cold enough for it to fall as snow. And so we actually expect to see a slight uptick in snowfall, perhaps for the upcoming decade or two. But there is a difference between snowfall and snowpack. We're seeing a lot more inconsistencies with snowpack because even though you get a really great snowfall, it melts in between or you get rain on top. And so there's issues, of course, when it comes to the ski industry. With respect to things like sugaring, so maple trees need to have that nice period in the spring of warm or above freezing during the day and below freezing at night. And so you have to have that nice diurnal range. And we are starting to see some changes to that. In Vermont and New Hampshire, we're starting to see springs that are not really changing a whole lot in temperature. So it's still been relatively cold, but then all of a sudden you kind of slam right out of spring into summer. So you go from, having below freezing temperatures to suddenly being in the 90s. In fact, that was something again that we saw this year. And so again, we're seeing those rather rapid changes. But we are expecting the sugaring kind of region, the sweet spot for that, to start shifting a little further north.
Thank you, Janelle. Our next one is from Nisa, and I'm going to go ahead and unmute you.
Great. Thanks to you both. This question was for Dr. Hanrahan. So drawing on your work with climate consensus, I'm curious what the top tips are that you would give either to citizens or to scientists in other disciplines about how to best communicate the science of climate change.
Yeah, Nisa, thanks for that. I think it's a really great question. And my response is just do it. As simple as that sounds, because really the problem, people right now trust scientists, right? People don't trust a lot of people. They don't trust politicians. They don't trust a lot of people, but they still trust scientists. The polls show that. And so if we are just willing to say, hi, I'm an expert in this, or I know a little bit of something about this and start talking about it, that is huge, because right now there are so many people out there that know nothing about climate science, or, even worse, want to spread a bunch of misinformation, and they are incredibly vocal right now. And so in my mind, part of the reason why we are where we are with this huge misunderstanding of the science, and why we're moving in my mind very much the wrong direction, is because climate scientists are trained to talk to each other in peer-reviewed journals and at conferences. And that's what we're good at. And that's what we're comfortable with, because giving a talk at a conference, once you are used to doing that sort of thing, is much more comfortable than trying to present to the general public. And so that's, in a nutshell, what I would say is just start doing it. And that's what we've been doing with our students, is we've been just giving them, and they make mistakes, I make mistakes, but you know what, my students are learning how to do it as they're learning the science. So my hope is that they're going to be much better about talking about it once they are kind of seasoned veterans with the science.
I have a question kind of related to that. In your, what advice would you give someone who wants to study climate science like you two have? And maybe in another way to phrase that question is, in your opinion, what is the most important area that a young person could start studying today to help mitigate and or adapt to climate change in the future?
Lisa, do you want to take that one since I've been talking a lot?
Well, I think the biggest issue is how to change people's behavior. And so depending on whether you want to approach that from a technical aspect about making it easier to conserve energy or to have a lifestyle that's acceptable without using quite so much carbon dioxide emitting type of energy, that would be one direction. If you are comfortable working with the sociology of people, then thinking about what actually transforms society, how to get people thinking with a different mindset about what the future could be or they want it to be. And it's not just about avoiding the risk of all the scary stuff. It's about actually being able to envision the direction you want to go and the lifestyle and changes that could make that happen. One of the things that in my local community, for instance, that I'm looking at is we've got this technology of electrical vehicles sort of coming up very, very fast. But I only know of one place where you can actually plug in an electric car in this area. And the same thing with biofuels. There is no good source for a diesel truck to gas up with biofuel north of Concord, in New Hampshire anyway, at least that I know about. So making those kinds of resources more available, more known, creating maps of places where these resources exist. You know, there's so many different directions that you could come at this need for change from. And I think you have to find your passion in it and also believe that it makes a difference. Very, very small changes make a huge difference, both in the way people perceive things, but also in the way the world responds. And a really good example of that is leaded gas. I look at lake sediments, right? In every single lake sample that I take, we can see an increase in lead in those sediments starting at about 1910 or so, when motorboats and also gas vehicles started driving around. We see lead increasing in those sediments deposited in the bottom of the lakes until 1974. And then by 1975, we see that starting to decrease. And in that year, that single year, 1974 to 1975, is when the US decided to take the lead out of gasoline. And immediately we saw the change in the level of lead being deposited in the lake bottoms. And that trend, that decreasing trend, continued. And so it doesn't take a lot to transform the natural world and to sort of correct things that were human created. What we don't have much control over is the things that we don't control. You know, we can't control hurricanes right now, despite what some people think. But we can control some of the things that trigger some of that.
Thank you. So we have another question from Kathleen. In a general public talk, how do you handle the comment, "I don't believe in climate change," in an argumentative way that disrupts all the other people in the room?
So I guess I'll take this one. And this is exactly why climate scientists don't often engage with the public. I actually gave my first public lecture. It was kind of like a climate change 101 about 5 years ago at Northern Vermont University. And we advertised all over the place. And the plan was to have me present, and my students were going to be on a panel to try to answer questions, just to give them that experience of doing it. And I was already really nervous because I had no idea who was going to show up. But I ended up having people picketing out front of where I was going to be giving my talk. And they ended up being people who were concerned about chemtrails, and I won't go into the connection there, which I actually didn't know ahead of time. So I had that, and I also had people who were simply saying, how can you, forecast the weather 100 years down the road when you can't even generate an accurate forecast within a week? And of course, some people just simply saying, I don't believe in climate change. And I wouldn't say that it was a really great event. I think it was good because it was a good experience for me, and it was a good experience for my students. But I have to say, it is really, really hard to try to rein that in. If somebody has a very specific criticism or a very specific question, you can address that. And with experience, that improves. But sometimes people are just combative. And so one thing that I've learned in my years, I guess, of researching kind of the social side of things is that there's a whole spectrum of people in their understanding and belief in climate change. So there's people who really understand the science and are very concerned and sometimes would say they're alarmed. And then there's the other end of people who are just complete deniers, and no matter what happens, they're never going to believe in the science of climate change. The vast, vast majority of people are somewhere in the middle. Those are the people that we need to be talking to. So this person over here who's shouting and screaming saying, I don't believe in climate change, it's important that you respond to them, but only if the other people are listening. And so that is an opportunity for you to communicate accurate science to all of those people in the middle. But don't ever think that you're going to convince your crazy uncle so-and-so that climate change is real if he is just adamant that it is not real and that it's a hoax or something. So don't waste your time with that, but just really work on those people who fall in the middle, which is the vast majority of folks.
Well said. I like that. Our next one is from David. I'm going to unmute you.
Hi. Are you, can you hear me?
Yep.
Yeah. Okay, I just wanted to mention that I've noticed lately that even though autos aren't wonderful things to use, be energy efficient, prices on solar energy have come down a lot. And I think that's great. That's all. That's all I had to say.
Actually, if I could just say that, respond to that a little bit, it kind of saddens me to see the cost of fossil fuel energies low, because it disincentivizes the alternative fuels. Alternative fuels are more expensive, and if you can get gasoline for less than $2 a gallon, you're not going to pay $2,000 to have a solar array put on the top of your house that year. And so it just delays the transformation unless people are really future planning to adapt. So, you know, until fossil fuel actually bears the true cost of the burden that it creates on society, it's going to be hard to wean ourselves off of those fossil fuels.
Thank you.
We have one from Donna. Do you have any predictions on how climate change will affect bird populations in the Northeast? How can they migrate through these intense storms or find feeding grounds along the way?
So I don't know for sure that I have an answer to that, but I do see the one right above asking me to share my last slide again with a list of references. So I'll do that while Lisa and I try to tackle this one, if that's okay.
I don't know a lot about birds, but I do have a biology background. And one thing that is important to understand about any animal that has to travel from place to place is that the timing of when those food sources become available is changing. And it's going to be a little bit tough for organisms to adapt for a while until they figure out that, oh, you know, the pollen of my favorite flowering plant is showing up earlier in those places that I expect it, but I'm not there yet. So, you know, when the butterflies come in or when the hummingbirds come in, you know, they have preferred food sources. And if the flower especially is not in bloom at the time that the organism arrives, because the flower is already done blooming and it's gone to seed, then that bird is going to have to find another resource. So the most important thing that I think people can do to help that adjustment is to protect a wide variety of habitat. So if, say, a hummingbird comes into an area and cannot find the food source because those flowers have already finished flowering, it can shift sideways and go partway up a mountain and find that. But if that mountain's been developed, if all of that area has been cut down or turned into lawn, then they're not going to find that food source there. So protecting habitat so that organisms can shift ranges as they need to adapt to that shifting timing of things, that's the best thing that I think we can do to help maintain the diversity or protect the diversity of organisms that we have.
Thank you, Lisa. And Donna, we do have a State of the Bird Red Barn series next week as well. So if you want more information about that, that's the one to join. I think we have time for one more question, if anybody has any last minute ones. This is from Bob and Sue. I'm going to go ahead and unmute you guys.
I was just wondering how exciting you must have been if there was one upshot of the lockdown. It was to see all over the world areas that had not witnessed seeing mountains and seeing wildlife in canals, and how quickly that phenomena was able to recover, and whether you see that as a tool for helping with your research and as far as, you know, impacts of, I mean, granted, it was pretty dramatic what we did, but it certainly showed the world very visibly the difference that we do make.
Yeah, I'd like to address that. Thank you for that comment, Sue. It's been really interesting for me because you know, I'm always talking to my students year after year about the amount of carbon dioxide that's in the atmosphere. And like I said, it ticks up about 5 parts per million every single year. And so it's always interesting every time I teach the class we always actually try to guess what the next point is going to be. And so I'm definitely interested in seeing, you know, how much additional carbon we're going to put in the atmosphere this year, because of course what has happened is absolutely unprecedented. Nobody's driving anywhere, nobody's flying anywhere. And so I have looked into this, and while it seems like we have to be putting a huge dent in this whole climate change story, the unfortunate truth is that we're actually not. And the reason why I say that is because even though the amount of carbon that we're going to put in the atmosphere this year will in fact be lower than it was last year, and probably for the last couple of years, the amount of carbon that's in the atmosphere is cumulative. And so it's analogous to filling a pool with a hose that has a very small, teeny tiny leak. And what we've been doing is we've been filling it with a fire hose, and it's been increasing every single year. And what we've done is we've turned down that fire hose just a little bit this year. And so we're still filling the pool, we're just not filling it quite as fast. So we're still absolutely walking into an unprecedented time, and unfortunately there's so much more that we need to do in terms of stopping our emissions, not just through transportation, but also the way that we heat our homes, the types of foods that we eat and where we get our food, and then ultimately we got to figure out how to make that slow leak much larger by pulling carbon back out of the atmosphere.
But it did show us that we do make a difference in a very dramatic way.
Yeah, hopefully people will listen.
Well, when I'm talking to my students, I use examples like this for reasons for hope. You know, this is a human-caused problem. It's not an asteroid or some weird cosmic ray coming and making these changes on the Earth, right? We created that, and therefore it's in human power to come up with a solution and change it. And these small changes that humans make, like the change in leaded gasoline, like the shutdown, like the gas crisis in the 1970s, we actually see a leveling out of CO2 increase in the atmosphere during that 1 year when there were long lines at the gas stations and price of gas shot up. So small changes that seem insignificant are measurable. The Earth is so sensitive to what we're doing that what we do can make an impact. And I find that to be a reason for hope, although sometimes it can be a reason for despair too when we go the opposite direction. But hope is the way I think we're going to change people's attitudes and mind. If everybody gives up and says it's too much and it's too hopeless, then then we're not going to get a lot of change. We'll just get some fatalism. But I would also say that I'm following this COVID crisis with great interest, because a lot of the same attitudes about the future are being mimicked by that refusal of the US to flatten the curve. So, you know, in Europe and a lot of the rest of the world, there's been a huge effort to try and control CO2 emissions. And similarly, those are the areas that have done a really good job of flattening the COVID curve. And in the US, where we just don't like to plan for the future with CO2 or anything else, we're having a great deal of time controlling this virus. So, you know, there's definitely a psychological association there. And if we can crack that nut, I think we'll make a lot of progress.
Well, thank you both. This has been great. And I'm really glad how well this went. It went very nice. I invite you all, if I may, Dr. Donner and Dr. Hanrahan, can I invite people to, if they have other questions, to email you?
Yep, absolutely.
Yeah, absolutely.
Awesome. Well, thank you all for coming, and I hope to see everyone again the next coming weeks.
Thanks all. Be safe.
Bye-bye.